So for the second part of week 2 here, we're going to look at chapter 4, which is numerical methods of describing data, or summarizing data numerically. In chapter 3, we organized the data and summarized it with graphs. Now we're going to summarize it with numbers. For an example, let's say we want to know the mean length of all the fish in Lake Louisville. Well, it's not possible to gather up every fish in the lake and measure their length. So we don't have a method of doing that. We don't know what that value is, and it can't possibly be known. We can't collect them all. At any given point in time, how many values are there for the mean length? Well, there's all sorts of different estimates for it. But how do we get a good estimate for it? We're trying to estimate a population characteristic. And in this case, it's not possible to get an exact value because you can't measure every fish in that lake. So that is a fixed value, but we just don't know what it is. It's unknown. So suppose we want to know the mean length of all those fish. What can we do to estimate it? Well, we're going to use a statistic. Remember, a statistic is found from a sample. We take a good sample. Remember, that representative sample is where the sample statistic is really close or equal to the population parameter. So we're going to take a sample. As you can see here, we didn't take every fish. We just took those that are circled, and we found their length, and we calculated the mean from that. So as we look at these data distributions, remember we talked about that dot plot where you had the values on the number line, and you put a dot above the values for each observation, and we stacked them up if there were multiple observations on that value. And we got them all in there. We drew that curve through the top dot in each column. And in most cases in natural data, it takes that bell-shaped curve. We call that the normal curve because in real life, that's the shape that data normally takes. Well, I might have another set of data that I'm going to put on that same number line. It might look like this. As we look at those two, those curves are approximately the same. It's just the center of the red one is here and the blue one is here. We've moved the center. So that's what we're looking at central tendency. Later on in this chapter, we'll look at what happens if their center is at the same spot, but the curve's just a different shape. It's less spread out or less dispersed. So we look at measures of spread or dispersion. So let's take a look at measures of central tendency. The first one we're going to look at is called the mode. The mode is the data value that occurs the most often. The mode is sometimes a struggle. Sometimes there's more than one value that's repeated the same number of times. So there can be more than one mode. Is it going to be 2 modes, 3 modes? How many are allowed? Some textbooks differ on this. Some textbooks say there's either one mode or there's none. Others say it can be bimodal. It can have 2 modes. Others give complicated formulas on, well, the size of the sample divided by whatever is how many modes you're allowed to have. In many cases, if there's many numbers that occur the same number of times, we say there's no mode. Or if there's no value that occurs more than once, there's no mode. This is often true of small data sets. The mode for numerical data is usually only useful for very large data sets. If we have a lot of numbers there, then the mode is usually valuable. The other place it's valuable is in categorical data. If we're the favorite color again, we can't calculate a mean of a color, but we can tell which one occurred the most often. So the mode is not used nearly as often as the mean and median. Let's talk about the median. The median is the middle value. It divides the data into half. So the median is in the middle of the data. Half of the values, half of the observations are smaller than the median. Half of the observations are larger than the median. To find this, the first thing you have to do is put the values, the observations in numerical order, from smallest to largest. So to find the sample median, the single middle value, there's 2 different cases here. If we have an odd number of items, n is an odd number, remember n is the number of items in the list. If n is odd, there's 1 value in the middle. If n is even, then there's going to be 2 values in the middle, and we have to average those 2 together. So let's look at a sample size of size n, where n is 5. So this is odd. There's an odd number of items in this list. The numbers are in order from smallest to largest, and n is odd. So we work our way in. N is the middle number in the list. Now, if it was a large list, crossing off the first and last and working our way into the middle wouldn't be very practical. So there's a better way of doing that we'll get to. Here, n is even. There's 6 items in our sample. We work our way in, and there's 2 numbers in the middle. So the median is between them. To find that, we add them together and divide by 2. 5 plus 6 is 11, divided by 2 is 5.5. The mean is the arithmetic average. This is that calculation we've done since like 3rd or 4th grade. You add them all up and you divide by how many are there. You use the Greek letter mu to represent mean. That is a population mean. If it's a sample mean, we use x bar. So x with the bar over it is pronounced x bar. So mu is a population characteristic. X bar is a sample statistic. Our formula for the mean, this little symbol here means sum. So you add up all the values and divide by n. So let's go to our sample of 6 here to find the mean. We add them all up. 3 plus 4 plus 5 plus 6 plus 8 plus 10. Then we divide by 6 because there's 6 of them. So those add up to 36. 36 divided by 6 is 6. Now, the next step is to find something called the deviates or deviations from the mean. How far does each observation deviate from the mean? Well, we're going to take each observation and we're going to subtract that mean of 6 from it. 3 minus 6, 4 minus 6, 3 minus 6 is negative 3, 4 minus 6 is negative 2, and so on. So we subtract the mean from each of those data values, each of those observations. The sum of these deviations, when we add them up, should always add up to 0 at this point. If they don't add up to 0, either we did something wrong, or maybe if we had a weird value of n, so we had to round the mean, that might be an indicator as well, that we might be slightly off 0 if that happens. And yes, that sum should always be 0, or again, if it's a rounded mean, it has to be very, very close. The mean is a balancing point, so the deviation should always add up to 0. So imagine a ruler with pennies placed at 3, 4, 5, 6, and 8. So if you place those pennies on that ruler, 3, 4, 5, 6, and 8, the point that would balance would be 6. If you put a little 6, 8, and 10, I should say, if you put a fulcrum or a piece under 6, it would balance there. So what's happens to the median and mean if the lengths are 10 instead of 10 here, we change that to a 15. For the median, we still work our way in, and it is between the 5 and 6. It's still 5.5. The mean, however, is changed. This doesn't add up to 36 anymore. It adds up to 41. We divide at 6.833. The mean has changed. This is called stability. The mean is more susceptible, more variable to changing one of the numbers, to a really large value or a really small value, where the median is more stable. Changing one of the values to a really large value didn't change the median, but it did affect the mean. If we go from 15 up to 20, well, the median still stays the same. It's still 5.5. The mean, however, has changed even further. So again, that mean is less stable. The median is a more stable measure. Some statistics are not affected by these extreme values, like the median. Some are. The median is resistant to that change. The mean, however, is affected, so it is not resistant. It is variable with those changes, strongly affected. Suppose we caught a sample of 20 fish now, And we're going to create a histogram of their lengths with a class width of 1. There's the histogram that would represent this sample down here of 20 fish. Calculate the mean and median. Well, the median, if we put them in order from smallest to largest, is 6.5. Notice this is a perfectly symmetrical distribution. The median should be right in the middle. If that is a perfectly symmetrical distribution, the mean will also be in the middle. If it is a symmetrical distribution, the mean and median will always be equal. Now we're looking at 20 fish. We're going to create the histogram. Notice this one is not symmetrical. It is severely skewed to the right. Our mean and median, the median is right there. Half the data values are smaller, half are larger. The mean, however, is more strongly affected by those large values. If the mean is larger than the median, the data is skewed right, or skewed positively. Let's look at a set here now. If we look at our histogram, it's skewed to the left. This left tail is stretched out. The opposite will be true. If we calculate the mean and the median, now the mean should be smaller than the median, and it is. If the mean is smaller than the median, the data is skewed to the left. So to recap, symmetrical, the mean and median should be equal. It is skewed if the mean and median are different. The mean will be away from the median in the direction of the skewness. If the mean is larger than the median, it's skewed positively or to the right. If the mean is smaller than the median, it's skewed negatively or to the left. Symmetrical distribution, you should report a mean. So if it is a symmetrical distribution, we just say the mean. We know that the median is close to that. If it is skewed, however, the median is more accurate measure of center. A trimmed mean. A trimmed mean is to remove outliers or unusual values from the data. To calculate a trimmed mean, we first have to figure out which values to take off. So we multiply the percent to trim by n. So truncate that many observations from both ends of the distribution when they're listed in order from smallest to largest. Then calculate the mean with the smaller data set, the points that are left after we've trimmed it. So for this data set, we have 10 values here. The mean is 23.8, but we're going to do a 10% trimmed mean. Now here, n equals 10 because there's 10 items in the list. 10% times 10 is 1. That means we're going to trim one item from each end of the list. The smallest number and the largest number are trimmed off. So this has been trimmed 10% on each end. We calculate that new mean, it is now 22. That's telling us that if the trimmed mean is smaller than the regular mean, that means this was skewed to the right. If the regular mean is larger than the trimmed mean is going to most likely be closer to the median than the standard mean. So the difference between the standard mean and the trimmed mean is same as the difference between that standard mean and the median. It indicates skewness. What values are used to describe categorical data? Well, suppose that each person is in a sample of 15 cell phone users is asked if he or she is satisfied with their cell phone service. So they're going to respond yes or no. Well, we can put that in, we can do a sample proportion here, whereas what is the proportion or percent of people who are satisfied? The symbol we use here is P with a little hat over the top. It's called P hat. There are 9 that are satisfied over 15 total. 9 divided by 15 is 0.6. So we'd say that's a proportion of 0.6 or a percent of 60% who are satisfied with their service. The population proportion is P. The sample proportion is P hat. Now we tend to get a little sloppy in statistics and just say P anyway, because again, we can never truly know that population proportion. So next we're going to study variability. Why is variability important? Well, there's variability in virtually everything. It's not a perfect world, so we can't make things from one to the next be exactly identical. There's going to be slight differences between them. Those differences are the variability. For example, does every can of soda have exactly 12 ounces? Of course not. Some have a little bit more, some have a little bit less, because the machine that does it isn't perfect. A little drop might be caught in the nozzle, so a little less gets in one. Well, that drop comes out in the next one, so there's a little more in the next can. So variability allows us to distinguish between usual and unusual changes. We expect a little bit of changes in that volume being put in that soda can. So when we're weighing those cans coming off the line, we've got to be able to tell, is this normal variation or is it too much? Is something gone wrong? We have to go back and recalibrate or check for an error in our system. Reporting only a measure of center doesn't provide a complete picture. It shows where the middle of that bell curve is, but it doesn't tell us how wide or narrow that bell curve is. So like here, these are 3 data sets, 3 dot plots. They all have the same mean and median, but they look very different. In fact, we're going to talk about range here in a little bit. These first two both have the same range, but again, I would say that there's very different variability in them. So different measures of variability. The first and the simplest is the range. The range is just the largest number minus the smallest number. So for these, both of these first two sets have a range of 50. 70 minus 20 is 50. Those first two both have that same range. The second one is 50 minus 40, or only 10. So it's pretty obvious using just the range that this last one has less variability than the first two. But the range does not distinguish between these first two sets. And I would say there's definitely different variability. The top one is more spread out than the bottom one. The bottom one's more concentrated in the center there. Other measures of variability, we start with those deviations that we calculated in our table before when we had the mean. So the first step is going to be to find the mean of all of those values. Remember, when we add up the deviations, we get a sum of 0. It's one way to double check after that second step of our calculation. What we want to look at, though, is there a way to find an average deviation? Well, if they add up to 0, the mean deviation would always be 0. So we need to find a way of making it so they don't, to measure how big they are, and either regardless of what direction they are from the mean. So the estimated average of the deviations squared is called the variance. So we square the deviations so they're all positive. That way they're not going to add up to 0. They're going to add up to some positive number. So the variance, for a sample variance, we use the symbol s squared. For a population variance, we use little sigma squared like that. It goes with the symbol, the sum of the deviations squared divided by n minus 1. This is for a sample. If it were a population, it would be just n on the bottom instead of n minus 1. That is degrees of freedom. The reason we say it's n minus 1 is because if we know all of the numbers in a data set except one, and we know what the mean is, the last one is already determined. There's only one value it can be, so it's not free to vary. So, yes, as I said, the population variance is denoted by the sigma squared rather than s squared. This is a sample variance with the s squared. So let's say we want everyone in the class caught a sample of 6 fish from the lake. What would each of our samples contain? Would each of our samples contain the same fish? Well, hopefully not. Would our mean lengths be the same? Well, most likely not, because they have different samples. They should be close, though, if we took good samples. But they would have different ranges as well as different means. When calculating sample variance, we use degrees of freedom, n minus 1. This is because the denominator of n, instead of a denominator of n, because it tends to produce a better estimate. Like we said, there's a deep theory behind it, but the simple way of explaining it is if we know the mean value, then the last value of the set is always predetermined. So there's only n minus 1 values that are actually truly free to vary from the mean. So degrees of freedom will be revisited in Chapter 8. So let's actually look at calculating a variance here. So we go back to our set of data points here where we found that mean of 6. And we subtracted 6 from each data point to get those deviations. 3 minus 6 was negative 3, 4 minus 6 was negative 2, and on down the line. 10 minus 6 was 4, and so on. We noticed the sum of those deviations was 0. Next step is we're going to square those deviations. Now, careful on your calculator. Negative 3 squared should be a positive 9. Negative 2 squared would be a positive 4, and on down that line. These will not add up to 0. We add those up. That is the sum of the squared deviations, 34. Now we're going to divide that by 5. Why do we divide by 5? Because for this data set, n equals 6. There are 6 numbers in this set. Remember, we are dividing by n minus 1. So 6 minus 1 equals 5. So we're dividing by 5. (34) divided by 5 is 6.5. So the variance, s squared, is 6.5. Measures of variability. So the square root of the variance is called the standard deviation. So in that last set, s squared of the variance was 6.5. We square root that, we're going to get the standard deviation. The typical deviation from the mean, or what's often called the average deviation from the mean, is the standard deviation. What it's measuring basically is, on average, how far is each value from the mean. So if s squared is 6.8, the square root of 6.8 is 2.608. So on average, our values are 2.608 inches from the mean. Now they did a misprint here. They said 6.5 here, and on the next page they put 6.8. I caught that difference as well, but whatever your value for the standard or for the variance is, you will square root it to get a standard deviation. Calculate a calculation of a sample deviation or standard deviation of a sample. Again, that formula, this just means you're going to subtract the mean from each number. This means then you're going to square each of those. This part means you're going to add those up. Then you're going to divide by 1 less than the number that's there. Then you're going to take the square root. Now remember, this is the formula for S, the sample standard deviation. If it were a population standard deviation, it'd be denoted by sigma, and the denominator would not be n minus 1, it would just be n. This is the most commonly used measure of variability. The mean is the most commonly used measure of center. Another measure of variability is called the interquartile range, or just IQR. And it is the size or the range of the middle half of the data. To do that, we have to find quartiles. The lower quartile, or first quartile, is the median of the lower half of the data. So we found the median that cut the data in half. Half was smaller. We take that smaller half and we find the median of it. That is the first quartile. The upper quartile is the median of that larger half of the upper half of the data. So we take that half that's larger than the median, and we find the middle of that set. That's the third quartile. Interquartile range is Q3 minus Q1. What advantage does this have? Well, it eliminates those really extreme values on the outer ends. So if you have a really small or really large value, it does not affect the interquartile range. So here's a list of numbers. Let's find the interquartile range. Well, we're going to put them in order from smallest to largest. Then we're going to find the median. There's an odd number of items in this list. What is there? 1, 2, 3, 4. There's 51 numbers in the list, so the 26th value would be the middle. 25 on each side, so 26 is our median here. Now we take the lower part from 17 up through that. There's 25 values in there, so the 13th value would be in the middle. That's going to be the 24. That's the lower quartile. Now for the upper quartile, we're looking at the numbers that are larger than our median. Again, the middle value there is going to be the 30. Those are the quartiles. The interquartile range then is found by taking the upper quartile minus the lower quartile. 30 minus 24 gives us 6. From these quartiles in the interquartile range, we come up with another graphical display of data called a box plot. It's easy to construct because it just uses what's called a 5-number summary. It's one way of identifying outliers. We'll look at how we handle outliers in the box plot. And it's not subjective. It is very concrete. A histogram is subjective, remember, because when we're dealing with continuous data, we have to group it together into groups. Well, the way you group it can affect the shape or the appearance of that histogram. We can use this with medium or large sets of data, usually bigger than 10, mainly because if the data set is smaller than 10, the quartiles are really kind of not really telltale at that point. There's not a great breakdown of the data. And we can use comparative displays. We can put more than one box plot on the same axis, and it's easy to compare one data set to another. So let's look at a box plot. It's used for univariate data, so only one variable. And again, we want to make sure that we have a size that's 10 or larger. Let's talk about first how to construct what's called a skeleton box plot, which is a basic box plot. We find that 5-number summary that I mentioned. We draw a horizontal or vertical scale. Usually we do horizontal. It's a number line. We construct a rectangular box that goes from the first quartile up to the third quartile. We draw lines then to represent the median in the middle of that. And then we also draw lines out from the first quartile to the smallest value and from the third quartile up to the largest value. And each section of the box plot represents 1/4 of the data points. So we can see how spread out it is in each individual section of the data. So here's our data set again. We had the median of 26, lower quartile of 24, upper quartile of 30. We're also going to need the smallest number of 17 and the largest number of 47. So we're going to construct a number line that goes from 17 to 47. You can see this goes past 17 and 47 on each end. We're going to draw a box that goes from Q1 to Q3. So Q1 was 24, Q3 is 30. That box goes there. We're going to draw a line in for the median at 26. Then we're going to draw lines out to the minimum and maximum value. Those are called our whiskers. That's our box plot. Smallest value is at 17. Largest value is up here at 47. To modify a box plot, we want to account for outliers. We said a box plot was really easy to identify outliers. To do that, we start out with the IQR, the interquartile range. An outlier is any value that is more than 1.5 times the interquartile range away from either of the quartiles. So we use the lower quartile minus 1.5 times the interquartile range to find what's called a lower limit or a lower fence. We use the third quartile plus 1.5 times the interquartile range to get that upper limit or upper fence. Anything that is outside those limits is an outlier. And it's considered an extreme value. It's very extreme if it's more than 3 interquartile ranges outside. We typically don't deal with that, though. That's a very extreme value. So we can modify the box plot to show these outliers and to adjust them from our data set. So here's our set again. We have our box plot. But now before we put on the whiskers, we determine what those fences are. The lower fence here, the interquartile range was 6. 1.5 times 6 is 9. Our lower quartile of 24 minus 9 is 15. Any values less than 15 would be an outlier. Well, here, 17 is the smallest number, so there's no outliers on the lower end. There's no number smaller than 15. 1.5 times 6 is 9 again. Our upper quartile is 30. 30 plus 9 would give us an upper limit of 39. Well, there is a number larger than 39, so that 47 is bigger than 39. It's beyond the upper fence. That's going to be an outlier. If it was 3 times away, 3 times 6 is 18, 30, or upper quartile plus 18 is 48. Anything beyond that would be an extreme value. Since the 47 was an outlier, we're going to place a solid dot at 47 to mark it. Then we're going to trim our whisker. Our whisker now goes up to just the next value. The next smaller value from 47 was 38, so our whisker goes up to that next value after we've eliminated the outliers. So you see the whisker is trimmed. With that off, now it looks much neater. You can see that it's not nearly as variable. Before, when that whisker went all the way out, this section of the data was extremely spread out because that's a quarter of the data, but it covers a large range on our number line here. Whereas this part here is a very narrow range. It's still a quarter of the data. The data is very tightly packed there. Well, when we take out this one outlier out here, we can see a quarter of a data minus that 1 point fits in there. It's not really as spread out as it looked. It was that one outlier that was making it look way more spread out in that upper quarter. So the distribution looks better that way. So let's describe the distribution of percent of the population with a bachelor's degree or higher for the U.S. states and the District of Columbia is positively skewed. Having an outlier on the upper end makes it positively skewed. The median is 26, the mean with a range of 30. So that's one way of describing that distribution. The positive skew was, again, because there was an outlier on the upper end, or the positive end of the data. We can see how different histograms would give different box plots. Here, a uniform histogram like this, it's just a rectangle. All 4 sections of that box plot are exactly the same size. This is bimodal. Kind of does the same thing. It depends on how big each mode is. When it's like this, where it's empty in the center, you can see the outside edges. Those are smaller, which means the data points are more concentrated there. The larger sets here says that the data points are more spread out. Now these first 2 are identical, so a box plot cannot distinguish between a bimodal data and a uniform set of data. Here, however, this is what fits our box plot. This is what the histogram would look like for this. Remember, where the higher bars are on the histogram, that section of the box plot is smaller because the data points are more concentrated together. This is a skewed histogram here. Notice one of the whiskers is a little bit longer in the direction of the skew. So that right whisker is a little bit longer, so this is skewed right, or skewed positively. Here we can compare several different data sets on one axis. This is called a comparative box plot. This is looking at the salaries. So we can see here very quickly the Knicks have the highest average salary, but the Lakers have one person that's way up here. That's an outlier for them, but they do have the highest paid person of any of those teams. So you look at the similarities and the differences in those graphs. The lowest paid player on each team is pretty close to the same. To interpret center and variability, we have different rules. Chebyshev's rule is used to describe any distribution, regardless of the shape of the distribution, where k is always greater than 1. K is the number of standard deviations away from the mean. K is sometimes referred to as a z-score. Let's say k is 2. So that means we're going from our mean. We're going to go out 1, 2 standard deviations to the left, and 1, 2 standard deviations to the right. So we're making that range that goes 2 standard deviations in each direction from the mean. So k equals 2. We put 2 into this formula for k. So it's 1 minus 1 over 2 squared, which becomes 1 minus 1/4, which is either 3/4 or 0.75, times 100 makes it 75%. We would expect 75% of the data in this set, in any set, to be between 2 standard deviations smaller than the mean to 2 standard deviations larger than the mean. So this rule can be used with any distribution, no matter what the shape. For a sample of families with 1 preschool child, it was reported that the mean child care time per week was 36 hours with a standard deviation of 12. Chevyshev's rule says at least 75% will be within 2 standard deviations of the mean. 2 standard deviations to the left is 36 minus 12 is our standard deviation, so minus 2 times 12. That gives us 12. To the right side of the mean, or the greater side, is 36 plus 2 times the standard deviation. 2 times 12 is 24, 36 plus 24 is 60. So we expect 75% of all the children in daycare to be between 12 hours and 60 hours a week. At most, what percent of the observations would be greater than 72? Well, at least 89% would be between 0 and 72. Where does that come from? Well, 72 is 3 standard deviations away from the mean. 36 plus 3 times 12 is 72. So it's 3 standard deviations above. So k is going to be 3, so it'll be 1 minus 1 over 3 squared, of course, times 100. 3 squared is 9. 1 minus 1/9 is 8/9, or 0.888, or 0.89. Times 100 is 89, 88.9, or 89%. So at most, well, we'd expect at least 89% to be between 0 and 72. Well, nobody's going to be less than 0 hours a week. Nobody can be negative. So 11% will be more at most. So let's look at what's my area here. Input the following command into a graphing calculator in order to graph a normal curve with a mean of 20 and a standard deviation of 3. So you do y equals normal PDF, x 22 or 20, and then 3. We're going to set our window from 3 to 20. So I'm going to end my slideshow here so I can pull up my graphing calculator. So we're going to enter here in the stat plots, or in the plots, I should say, y equals second distribution, normal PDF. We're going to go, oops, I got to find my entry here. There we go. X, 20, and 30. So our X value is just going to be X, put in our variable. Our mean is 20. Our standard deviation is 3. We're going to paste this in. Notice there we got that. Let me try that again. Oh, I had it entered correctly. It didn't show up on the screen because it was running off the edge of the screen. So there it is. It looks like it just says DF for degrees of freedom, but that is normal PDF. We're going to set our window from X is going to go from 10 to 30. Doesn't specify a scale, so we're not going to worry about that. I'll put it at 2. Y is going to go from 0 to 0.2. Our Y scale, we'll put it at 0.05 for now. And let's graph. Let's trace it. So you can see it's going to trace out that bell curve, or our normal curve. We're going to use the trace command. Seven is going to be integral. That's going to find the area under the curve. If you haven't had calculus, that's an integral. Finds the area between the curve and the x-axis. So we're going to use that 7 command. And let's go to an upper limit of 23. Notice that gives us that area of 0.08. So if we did that for each of these here, it's going to give us those same probabilities that we saw with the empirical rule. that we saw with Chebyshev's theorem. The empirical rule, though, is a little bit more specific. It's specific to those normal distributions. So here we can see 68% is between one standard deviation below the mean. Oops, get back here. Got to turn my inking back on. One standard deviation below the mean and one standard deviation above the mean. 95% is between two standard deviations below and two standard deviations above. 99.7, or almost all of it, are within three standard deviations, three below to three above. That's the basic empirical rule. So if the height of a male student at PWSH is approximately normally distributed with a mean of 71 inches and a standard deviation of 2.5. So that means we have this bell curve. 71 is in the middle. If we go 2.5 this way, that's 68.5. Another 2.5 would be 66. This would be 62.5. Going this way, one standard deviation would be plus 2.5 would be 73.5. Next would be 76 and 78.5. So we just added 2.5 inches each direction, or subtracted going to the left. That's steps of one standard deviation. Now I'm kind of reading through the ink here. I inked over. What percent of the male students are shorter than 66? Well, 66 inches is right here. We would expect 95% to be between two standard deviations of the mean. So the other 5% is outside of that. It would only split half and half since it's symmetrical. So 2.5% would be down here. Taller than 73 inches, 73.5. 73.5 is right here. Let me get rid of some of this mess. Change color. So that is one standard deviation away. We expect 68% to be within one standard deviation, so that remaining 32% is split to each side. So 16% would be on this side. This one was 2.5%. Between 66 and 73.5, well, that's a little bit trickier. We just expect 68 to be between 68.5 and 73.5. So we need to add in this piece here. That piece is going to be the difference between the 95 and the 68 on just the one side. So difference between 95 and 68 is 27. We split that in half, it's 13.5% on each side. So 68 plus 13.5 is going to give us 81.5% there. You can see those match up with what they have. A measure of relative standing, or a measure of position. The main one we use is called the z-score. Z-score tells us how many standard deviations a value is away from the mean. Now, you mentioned with Chebyshev's rule, the z-score is really the number of standard deviations we are on each side of the mean. So the calculated z-score is the value minus the mean, then take that difference divided by the standard deviation. It's also sometimes called a standardized score. So what do these z-scores mean? Well, negative 2.3 means that value is negative, means it's below the mean. 2.3 means it's 2.3 times the standard deviation below the mean. 1.8, it's positive, so it's above the mean. It means it's 1.8 times the standard deviation above the mean. Negative 4.3 is 4.3 standard deviations below the mean. That would be a very unusual value. So Sally is taking two different math achievement tests with different means and standard deviations. The mean score on test A is 56 with a standard deviation of 3.5, while the mean score on test B is 65 with a standard deviation of 2.8. She scores 62 on A and 69 on B. Which did she score better? Well, those are different tests, so we can't compare the 62 to the 69 directly. We have to compare them back to their own populations, and we use the z-score for that. For test A, the z-score is 1.714. We took her score of 62, subtracted the mean of 56, got that difference of 6, and divided by the standard deviation of 3.5. So the 1.714 is saying on that test, Sally scored 1.714 standard deviations greater than the mean. For the other test, we took her score of 69, subtracted the mean of 65, divided by the standard deviation of 2.8. Her z-score is 1.429, meaning she's only 1.429 standard deviations better than the mean on that test. So her score on test A is the more impressive, although both of them are pretty good. Another measure of position or relative standing is percentile. A percentile is the percent of the data that is smaller than the given value, or is equal to or smaller than the given value. So here, if this is 90%, this value here has a percentile of 90. It's the 90th percentile, because 90% of the data is smaller than it. So let's say we have this list of head circumferences here in order from smallest to largest. There's 7 items here. This is the 5th percentile because there's nothing smaller than it, but there's one equal to it. So we'd say 5% of the data is smaller than that value. So what this is listing out is, actually I should be careful. These are not data values, these are benchmarks. So what this is saying is the 5th percentile of that data set. There's a lot more numbers in the data set, but the 5th percentile is 32.2. So that's saying that 5% of babies have head circumferences that are equal to or less than 32.2. The 50th percentile is saying 50%, or half of babies, have head circumferences that are equal to or less than 35.8. So what percent of the newborns should have a head circumference less than 37? Here's 37. 75% of babies will have a head circumference less than 37. This is asking greater than 37, so that means only 25% would be greater. 10% of newborn babies have a head circumference bigger than what? Well, our 10th percentile here is the 33.2. But that's saying 10% smaller than that. We want 10% bigger. So that means 90% would be smaller. So we're looking at the 90th percentile. Only 10% would be bigger than 38.2. That is it for Chapter 3. Please let me know if you have any questions. Otherwise, we'll go through this more in our online office hours.